Video we are discussing about vibrational or IR spectroscopy. In the previous video we have said about rotational spectroscopy and the various topics coming in that topic. We have already completed rotational spectroscopy. Now we are going to vibrational spectroscopy or IR spectroscopy. In this video, in vibration and IR spectroscopy, we will cover first simple harmonic oscillator. In simple harmonic oscillator, we have to study selection rules, energy levels and spectrum. This is the first part we should mention, and the second one is anharmonic oscillator. In anharmonic oscillator section, same we will study the selection rule for vibration and energy levels, then fundamental vibration, overtones and hot bands. These are the topics we are planning to cover in this video. So first we talk about what is vibrational spectroscopy. So each spectroscopy deals with some of the radiation in electromagnetic radiation. As we have mentioned in rotational spectroscopy, for a rotationally active molecule undergo rotational spectroscopy when the radiation is microwave. So microwave radiation is responsible for rotational spectroscopy. Like that, in vibrational spectroscopy, the radiation used is IR. That's why it has another name of IR spectroscopy. That means for a vibrationally active molecule like AB, let's say a molecule AB, when it is present in ground state and when we irradiate that molecule with some IR radiation, it absorbs the IR radiation energy and will excited to higher excited state, and it starts to vibrate with a frequency corresponding to energy of that level. That means each level have some specific energy. For representing the levels, we use the letter V, which represent vibrational quantum number. So for the ground state we will write V equal to 0, then V equal to 1, V equal to 2, V equal to 3. In rotational spectroscopy what we have seen is the letter J, which is rotational quantum number, and we said about J equal to 0, J equal to 1, J equal to 2, etc. Like that, here in vibrational spectroscopy the quantum number is represented as V, vibrational quantum number. V equal to 0 represents the ground state and V equal to 1 first excited state, then the higher states are written like this. So when IR radiation hits on the molecule, if the molecule is vibrationally active, it will absorb that radiation and go to higher energy level and starts to vibrate using that energy with a energy of that level. That means the molecule's energy is determined by the energy level in which it is staying. So each level has corresponding energy. For that means for the ground state there has an energy E0, then E1, E2, each level has some energy. So that we will look in the topic energy levels. Vibrational spectrum or IR spectrum is that which the spectrum or the peak we are going to get by absorbing some radiation. What is the energy corresponding spectrum we are going to get? For spectrums, generally x-axis contains either energy or lambda or mu bar in the x-axis, and the y-axis indicate the intensity. Then first let's talk about the selections rules. Before we have partitioned the topic as simple harmonic oscillator and anharmonic oscillator. Let's see what that means. That means for a molecule AB, we think like the molecules vibrate means its bond length increases and decreases, which is considered as vibration of molecules. So the vibration may be either stretching of that molecule or bending of that molecule. So changes occur in its bond length and bond angle. For such a vibration, we consider it as an oscillation and compare it with a simple harmonic oscillator. What is a simple harmonic oscillator? We know any oscillator or an object that oscillate by obeying the Hooke's law is known as simple harmonic oscillator. That is, any oscillation which obey Hooke's law is considered as simple harmonic oscillation. So what is Hooke's law states? For simply understanding the simple harmonic oscillator, we consider the spring, working of a spring, which is an example for simple harmonic oscillator. For this spring, let we consider the equilibrium position of the spring is here. When we apply some force F applied in this direction, according to Hooke's law, it is stating that some force corresponding to this applied force is developed in the spring in the opposite direction of the F applied, which is known as F restoring force, which causes the going back of spring into its original position after stretching. So according to Hooke's law, it states that the restoring force F restoring will be proportional to the displacement x. Displacement x means the change in distance after stretching, that is considered as displacement x, which will be so the restoring force will be directly proportional to displacement. So to change the proportionality sign, we multiply with the constant k and x. And one more thing is there, as the restoring force is developed upward, but the displacement, as spring is stretched down, the displacement occur downward. So both are in opposite direction and there will be a minus sign also. So this is the equation for restoring force. Then the F applied will be opposite of what is the restoring force. Then F applied will be equal to positive Kx. Then we have to find the potential energy of this simple harmonic oscillator. We will get integral F dot dx equation. We will use 0 to x because potential energy is force into displacement. So in the place of F we have to put F applied, which is positive Kx dx. So integrating this, we will get half Kx square. Simple derivation we have already studied in small classes. So we get potential energy as half Kx square. So we know that for any function that depends upon x square value, its plot will look like parabola. That's why when we plot the potential energy versus displacement of a simple harmonic oscillator, we get a curve like this or plot like this. So same is the concept of a molecule which undergoes simple harmonic oscillation or simple harmonic vibration while stretching or while applying some IR radiation. For a molecule AB, if R equilibrium be the bond length of that molecule, and on stretching or on undergoing vibration, its distance between two nuclei or the internuclear distance changes to R, then the displacement x can be written as R minus R equilibrium. Okay. Then for a molecule oscillating as a simple harmonic oscillator, the potential energy versus R minus R equilibrium, that means that displacement factor will give a plot like this, which is the graph of x square functions. So that's why while we studying vibrational spectroscopy, we consider this energy diagram, and the vibrational levels are indicated inside this plot. So the first vibrational level, which is V equal to 0 ground state, comes not here, but here it will come V equal to 0 level, the ground state we can say. Then V equal to 1, then V equal to 2, like that it will go for a molecule undergo IR spectra. Go to the selection rules. There are two types of selection rules are there. One is regarding which molecule can undergo vibrational spectroscopy or which is vibrationally active. It is stated that the molecule which show a change in dipole moment after vibration or after stretching or bending will be vibrationally active or IR active. So the first selection rule is regarding to select which are the molecule that can undergo IR spectroscopy. That is, the molecule should show a change in dipole moment after its vibration. And the second selection rule is according to the transition, is regarding the transitions, from which level to which level it can undergo transition. That indicates delta V should be equal to plus or minus 1. That means the 1 unit different transitions are possible from V equal to 0 to V equal to 1, or V equal to 1 to V equal to 0, like that, V equal to 1 to V equal to 2. That means 1 unit the transition which show a 1 unit difference in vibrational quantum number is only allowed. That is, from 0 to 1 is possible, and 1 to 0 is also possible. From 1 only to 2 is possible, not to 3 is not possible. So which is indicated by the selection rules. So to find which molecules are IR active, we simply look whether it show a change in dipole moment by looking the dipole moment before its vibration and after its vibration. For example, take a molecule hydrogen. For hydrogen molecule, we know that its dipole moment is 0, because for it the electronegativity towards each nucleus is same. For the electron dragging effect to this side will be same as to this side, so both will cancel out and the dipole moment is 0. On the other hand, while we considering a molecule HCl, we know that as chlorine is more electronegative, the electrons are more pulled towards chlorine and less pulled towards hydrogen, so it have a dipole moment. Now we will check that a change in dipole moment, not the value of dipole moment we are looking for. There should be a change after vibration. So after vibration means if we are stretching this hydrogen molecule, its bond length increases, it will look like this. And then also, while we consider a center here, the dipole moment is same, because both the atoms are same, so electron dragging or electron pulling effect is same for both sides. So here also the dipole moment is 0. So before vibration it is 0 and after vibration it is 0. That means no change in dipole moment, no change in dipole moment, which means it is IR inactive. And for this molecule, this indicate there is a net dipole moments towards right side, say some value x. Then after vibration, this bond length again increases. So while considering from center also, same effect towards right side, there is some increase in dipole moment. Value of dipole moment changes according to the distance from the center. So for this the dipole moment value is different, and for this distance it will be different. So the dipole moment value for this molecule will be different from this x value, say y. So there is a change in dipole moment, so the molecule HCl is IR active. So simply we can say that the molecules like hydrogen, that is homonuclear diatomic molecules, are IR inactive, and heteronuclear means both atoms are or both nucleus are different. For heteronuclear diatomic molecule, the molecule will be IR active. We have completed the selection rules part. Now we go to the energy levels corresponding to each levels. For that we are drawing the vibrational energy levels. V equal to 0, V equal to 1, V equal to 2 are the different levels, and each level have a different energy, say EV. So using the quantum mechanical derivations from Schrodinger equation, it has found that the vibrational energy is equal to EV is equal to V plus half into h nu, where V is the vibrational quantum number and h is the Planck's constant. V is the vibrational quantum number, h is the Planck's constant 6.626 into 10 raised to minus 34 joule second is the unit, and nu is the vibrational frequency. That means the frequency with which the molecule vibrate or the molecule stretches. So while we considering the unit of EV, how to find the unit of EV? Check each factor of the equation. V is an integer, as we know, V equal to 0, 1, 2, 3, all are integers, no unit. For H, the unit is joule second, and for frequency the unit is second inverse. So second and second inverse will be cancelled out. So the energy of each level will be in joules. So joule is the general unit for energy. But in some questions we can see energy as in terms of centimeter inverse. So how it comes? Because we know EV is equal to V plus half h nu, and this h nu is replaced by V plus half into nu bar. H nu is replaced by nu bar. How it be possible? Because for h nu, type of correlation we will see in only in this spectroscopy topic, that is energy is h nu we know. Also in the chapters of spectroscopy we can see that energy is also taken as E equal to nu bar, where nu bar is the wave number or 1 by lambda. So if in question the energy is in joules, it means the equation is E is equal to h nu. But in the question, if energy is taken as some centimeter inverse value, it indicates they meant for E equal to nu bar equation. So to convert an energy in joules to centimeter inverse, some energy in joules into centimeter inverse, what we should do? This joules comes from E equal to h nu concept, and this centimeter inverse they are indicating E is equal to nu bar. So for this conversion, what we should do is divide with the h into c. When we divide this value with hc, both h will be cut out, and there comes mu by c, which is equal to 1 by lambda, which is equal to nu bar. So if in question energy is given as in terms of joules and answer is in terms of centimeter inverse, first we have to convert the energy in joules into energy in centimeter inverse. For that what we should do, divide the energy in joules by hc. This we should remember. We need it for some questions. At these things, because we know EV, vibrational energy, is equal to EV is equal to V plus half into h nu. Also we can write EV is equal to V plus half into mu bar. Both equation you should remember. Now we can find the energy of each level for E0. That means V equal to 0. Put 0 in the place of V. We will get half h nu. For E1, put 1 in the place of V. We will get 1 plus half into h nu. That means 3 by 2 h nu. For V is equal to 2. We will get 5 by 2 h nu. So when we plot it in vibrational levels, we can say that V equal to 0. In this plot, the y-axis indicate energy, as we have said already in this part. Potential energy versus displacement is this diagram. So energy is plotted in y-axis, and this indicate the displacement r minus r equilibrium, or simply say x. For V equal to 0, the energy is not 0. There is some value for energy. And what is that value? It is half h nu. It's some positive value. So it will come here. V equal to 0 levels comes here, because the energy is not 0. Energy has some value. Some value of energy is here. Then that value is half h nu, which is known as 0 point energy. So what is 0 point energy? 0 point energy is the energy of 0th level of vibrational levels. It has some value. That energy is not a 0, it's a non-zero value. And for V equal to 1, so half h nu is the first energy, and for V equal to 1, the energy is 3 by 2 h nu, and for V equal to 2, the energy is 5 by 2 h nu. For V equal to 3, we can easily say 1, 3, 5, then 7 by 2 h nu. So these are the energy levels. So within an SHO type molecule, that means a molecule oscillate in such a way that a simple harmonic oscillator oscillate. We said the selection rules. we set the value of energy or energy levels, and now we have to say the spectrum, how the spectrum will look like. For that we should look for the transition. We have said that if this is v is equal to 0, v equal to 1 and v equal to 2, like it go. The only possible transitions are with delta v should be plus or minus 1. That means while transition there should be a change in 1 unit. 0 to 1 is possible, but 0 to 2 is not possible. And 1 to 0 back, that is plus or minus 1. 0 to 1 is possible, 1 to 0 is possible. So to find that energy, say if we have to find the energy of 0 to 1 transition, v equal to 0 to v equal to 1 transition, how can we find the energy needed for this transition? It can be taken as for this level the energy equal to E0, and for this level the energy is E1. So the difference between these two energy levels will be the energy needed for this transition. So for a transition from v equal to 0 to v equal to 1, the energy needed or the energy gap between the two levels will be equal to E1. That means energy of first level minus energy of 0th level. We know energy of first level is 3 by 2 h nu. So 3 by 2 h nu, and energy of 0th level is half h nu. So 3 by 2 h nu minus half h nu, we will get h nu. And take a transition from v equal to 0 to, v equal to 1 to v equal to 2. How to find this energy for this transition? V equal to 1 to v equal to 2 it is going. So the energy needed will be found from what's the energy of E equal to 2 level and what's the energy of E equal to 1 level. The difference will be the energy for this transition. So the delta E 1 to 2 will be equal to the energy of E2 level minus energy of E1 level. So what's the energy for E2 level? It is 5 by 2 h nu. And for E1 level 3 by 2 h nu. So again we will get h nu. From both this derivation we can find that whether the transition is from 0 to 1 or 1 to 2, whichever be the transition, always the energy needed is h nu. So the energy needed for a transition does not depend upon the levels in vibrational spectroscopy. What we have seen in rotational spectroscopy, the value for delta E was 2b into j plus 1. That means from j to which j plus 1 it depends upon. That is, it depends on the value of j. But in the case of vibrational spectroscopy, the energy gap or the energy required does not depend upon any quantum number like b. Whichever be the transition, always the energy needed is h nu. Also we can state it like a general case of transition from V to V plus 1. How to find the energy needed for the transition from the level V, any V, we don't know the value of V to just one level up, V plus 1. What will be the energy needed for the V to V plus 1 transition? It will be equal to energy of V plus 1 level minus energy of Vth level. What is energy of V plus 1 level? We know for a level V, the energy is V plus half h nu. This is for the case of Vth level. So for Vth level, this is the energy. So for V plus 1 level, we should put V plus 1 in the place of V. So V plus 1 plus half into h nu. V plus 1 level, the energy will be V plus 1 plus half into h nu minus energy of Vth level, we know V plus half h nu. What we can take outside, V plus half is common in both. Here it will remain 1 h nu, here 1. Not like that. So what we will do, we can take V plus half H nu as one factor, and there is 1 H nu, V plus half H nu plus 1 H nu, and this minus V plus half H nu. So this V plus half H nu and this minus V plus half H nu will cancel out, and we will get H nu. Also you can check by giving this H nu inside. This is correct. We will get H nu by subtracting. So what does it mean? When the transition is from V to V plus 1 level, the energy required for V to V plus 1 level transition is delta is equal to H nu for vibrational spectroscopy. So whichever be the transition, the spectrum always will obtain that H nu value. So this is the energy part and this is the intensity or absorbance part. We will get a peak at E is equal to H nu always. So for the transition V equal to 0 to 1, we will get peak at E is equal to H nu. And for the transition V equal to 1 to 2, we will get a peak at E is equal to H nu itself. And for V equal to 2 to 3, we again get the peak at this value. So compared to other spectrums, vibrational spectrum will be look more intense because it's all the transition spectrum comes in only within one peak, because all energy required for all the transition is same. But for in the rotational spectroscopy, the case was different. For J equal to 0 to 1, we get the energy in the 2B level. For J equal to 1 to 2, we get at the peak at the 4B level, 4B energy value. And for J equal to 2 to 3, it was 6B. So the peaks were different for different transition. But for vibrational spectroscopy, the peak comes in the same position always for whichever be the transition. There are the things we have studied in rotational spectroscopy and in vibrational spectroscopy. In rotational spectroscopy, the radiation needed was microwave radiation, and for vibrational spectroscopy, the radiation required is IR radiation. And for rotational spectroscopy, the value of energy is given as Ej is equal to Bj into J plus 1. And for vibrational spectroscopy, energy for each level is given as Ev is equal to V plus half into H nu. Here J is the rotational quantum number and here V is the vibrational quantum number. And here the energy difference or the energy required for transition. This is the energy for each level, and this is the energy required for some transition, say from J to J plus 1, like that. Then that energy were QB into J plus 1 for vibration. That energy for simple harmonic oscillator type vibration, that energy required is from V to V plus 1 level is was H nu. There is no depending upon V value. And here the selection rule was for a molecule to be rotationally active, it should have a permanent dipole moment. Here the selection rule was for a molecule to be vibrationally active, it should show some changing dipole moment after its vibration. That means the dipole moment before stretching and after stretching should be a different value. And coming to the rotational quantum levels, we know that J equal to 0 and J equal to 1 were apart from a distance of 2b, and J equal to 2 was at a distance of 4b, and like that it was going. That means rotational quantum levels are not equispaced or equally spaced. Coming to the case of vibration, V equal to 0 and the distance between V equal to 1 was h nu. For V equal to 1 and V equal to 2, again the distance was h nu. So all the levels are at a distance of h nu. That means all vibrational levels are equispaced. So rotational levels are not equispaced, vibrational levels are. And for the case of spectrum, a rotationally active molecule will show spectrum for V equal to 0 to 1 at a value of 2b, 1 to 2 at a value of 1 to 2 at a value of 4b, and 2 to 3 at a value of 6b, where b is the rotational constant. At the same time, for a vibrational spectroscopy, for V equal to 0 to 1, the spectrum will be obtained at E equal to h nu value, some energy value. For V equal to 1 to 2, again the peak will be obtained at h nu. For V equal to 2 to 3, again the peak will be on the same position. Like that we can study each difference between rotational and